Hello and welcome. Do you hear me? Yep, good. Hello and welcome to lecture 3 about image features and filtering. So let's start with a quick recap from last 2 sessions. Last week we talked about images formation, how they are formed on computers, how we can use cameras to convert what we see in the environment to pixel values. And then we saw how we can model that using a pinhole camera model. We talked about digital representation and different color channels, RGB, HSV, and other color channels. And we learned how we can convert them, how we can do some Instagram-like filters on those images. So we also talked about geometric transformations, where we didn't want to change pixel values, but we wanted to change pixel locations. We wanted to do geometric transformations, such as rotation, for example. So we learned that there are 2 matrices, intrinsic camera matrix, and which we could use for skewing images, to add information from the focal length of camera, center of the image. And we also had the geometric transformation matrix, where we could change the location of pixels according to the transformation that we have in mind, like rotation, for example. We learned what pixel values mean, what grayscale values mean, why they are in the range of 0 to 255, because we had 8 bits, 1 byte for each color. So we call that intensity, and we had a value between 0 to 255. We talked about image resolution, and we talked about, in the section before, we talked about human brain, human eye, how eye works, and how we can, in the future lectures, we will see how we can learn from our brain more and more to model the environment and come up with better models like neural networks. So tonight we are going to talk about visual features, what they mean. Talk about edges, how we can extract the edges in an image. This is, for example, an edge. This is black, this is white. So this is an edge, this is a corner. We will see how we can find these points in an image. With kernel-based models, we will see what convolution means. And later, in lecture 7, we will learn about convolutional neural networks. So this is the building blocks. They are just coming, and then we will connect the dots. So we will talk about corners. We will briefly talk about color and texture and how they can be used to represent image. So basically, what is a feature? A feature is a property which we can use to describe an item. For example, you can say letters, they have features. Like if you say C, if you say cat, the way you recognize it is you know the alphabet. You know what C looks like. It has some features. It's a curvature. You know what T looks like. It's a line with a stroke on top and things like that. So these are the features that help us understand our environment. And generally, feature is a mark or a symbol that says something about the entity it describes. So for example, if you want to describe a laptop, you come up with some specifications of the laptop, the memory, the CPU, the RAM, storage, size of its LCD, and things like that. The same goes with a mobile phone. Usually they have cameras, they usually have good processors these days, and the power that is in one iPhone, like a 10-year-old iPhone, not a new one, is more than the computational power that was used to send humans to the moon. So you can imagine how powerful these devices are these days. That was a lot of power in that time, but it's now a 10-year-old iPhone, and it's too slow and it doesn't work really. So when it comes to computer vision, we don't care about the memory and RAM now. We are talking about visual features. What features are in images that help us distinguish them? So if I show you a few of these areas, like this box, will you be able to tell if it's a cat or a dog? Yes, but would it be enough to say if it's a wolf or a dog? Probably no, right? Because they may be more similar. But if you see just the eye, it definitely is not a human. So it has some features for you to help you understand what the object is. Sometimes these features can be enough, sometimes you need a combination of them. The same goes here. If you see this mouse, it's most probably a kitten, but if you see this ear, it could be several different animals. But now, these features that you see here are enough to differentiate a cat and a dog. And a cat and a dog is a classical computer vision problem because it's a very difficult problem. There are different breeds. It's not a simple task to say a cat and a dog. But would these features that we have here be enough to differentiate these animals? So we have two answers. Most probably yes, and most probably no. Who is most probably yes? So the question is, we have these features. Would they be enough to differentiate these animals? Most probably yes. Most probably no. Okay. So the answer is we should try it. We should see whether it is there or not, but I would say most probably yes. Why? Because also I don't have the exact ear type, but when I go and search in this image for this ear type, the most similar item I may find is probably this ear, which gives me something like a 60% similarity. But if I compare it to this image, it would give me something like 40% similarity. So this different number might help me to be able to differentiate these two different items. That is why nowadays we have something, an aspect called the global dictionary of features. So deep learning models nowadays, they look at like 1 million images, 10 million images from internet in different classes. One of the most famous data sets is called ImageNet. We will talk about it in lecture 7. We have ImageNet dataset. It has millions of images in thousands of categories. People train their models on these, and those features are extracted. They learn from these models. We will say how it works later. But once those features are extracted, then they do something called transfer learning. They use that model, those weights, on a different unseen data set. Like you use the models that are trained on natural images, and you use it for classifying cancer versus non-cancer. So those features are sort of universal. And the interesting thing is, we will see later, that the features that these models learn are very similar to the features that our brains learn. So as you remember, the kitten example that we had it in a box, in an environment that there were no horizontal lines, they couldn't see horizontal lines later. But if they have the vertical lines, then they can adjust, they can learn filters for horizontal, vertical, corners, different sorts of features. And we have similar cells in our brain. So once a baby is growing, because the interesting thing about vision is that the structure is built before birth, but it's never used because there is no light there. So once we are born, the eyes open, and then it starts getting programmed. That is why it is crucial. If someone is born blind, it is almost impossible to give them vision back in the future. But if someone has vision and then goes blind, if you fix the sensors, if you fix the structures that are now damaged, they will be able to see again. So that's a very, very important difference, because our brain is constantly learning. When a baby touches things, he's making sense of a 3D environment around it. They are understanding the haptic sense, the feelings that objects have, soft, hard. They understand the distance of the items. They understand what burns. They understand what hurts. And this is the way humans grow. So back to vision. So these features, most of the time, are enough, but we need more basic features. This is just for visualization. We do not have this luxury of finding these features and images because they are not easy to find and they are not that useful in the future. They are very, very fine-tuned to that specific image. We want something more general, like this example. You remember we read this text flawlessly last week. So you see that we do not necessarily need to have the same amount of data to understand the environment that we have been trained before. We can use the features that we have extracted in our mind. Our mind can now customize them and be able to read the text. So we read this before. Forget about these first lines and the last lines. These are marketing. Please share. You have amazing minds, but I don't see why. This is for marketing purposes, to share images so that they make more money. But apart from that, this message serves to prove blah, blah, blah. So we can read, we can understand our environment from less information. We don't need all the information around us. So now that we know about this, let's look at a very interesting and simple example. Face detection. This is part of your coursework, right? So pay good attention to these few minutes and you will have like 20% of your coursework done. So what we have here is we have a camera. And as soon as you open your camera, bring it up, it detects faces. How does it work? Like looking at Google Street View, it automatically blurs faces for privacy reasons. People don't want to be seen, right? So this is for privacy reasons. If they don't do that, then they have to stop the car, get consent from everyone. Are you happy to be online? Yes, yes, GDPR and things like that. So they just detect the face and blur it. But how do they do it? How do cameras do it? It's a very, very simple way to do it, and we will learn to do it tonight. The idea comes from HAR filters and integral images. What is a HAR filter? A HAR filter is something like this. The idea behind it is it says if you have a horizontal black area and it has a horizontal white area, let's call it dark and bright for the sake of this argument. If you have a dark area and you have a brighter area under that, there is a good chance that you are finding eyes. Right? We don't see that in the face a lot. This is mainly here. If you have a dark area and the bright area in the middle, it's probably you're detecting a nose, and so on. So once we combine a few of these together with a technique called cascading classifiers, which we will learn, or if you haven't learned in machine learning, you will learn in lecture 6, we will be able to come up with a set of rules. We say, if you see a dark area, a brighter area under it, now close to that area, you see two dark areas, a bright area in the middle, something like that, and so on, for different parts of the face, you are likely to have a face. So the idea was from a 1998 paper where they discussed HAR wavelets instead of using image intensities. And Viola and Jones in 2001 adopted this idea, and they came up with something called HAR-like features, and they have been cited tens of thousands of times. So with this idea for face detection, and because of using integral images, which I will tell you how easy it is to do that, this model is extremely fast, and as soon as you open your camera, it detects faces. So this is the way it works. They have a set of different filters which detect different areas on the face. But how does it work? Let's say this is the black or the dark, and this is the bright. So I represent the dark with -1 and represent the bright with 1. So what I do is I do an element-wise multiplication of this filter over different parts of my face, my image. Let's see an example. Let's say I'm looking at some random area, like my shirt. It's probably some values like this, right? So if you multiply these, -1 plus 250, -1 times 50, -1 times 90, 1 times 170, 1 times 70, 1 times 60. If you add them, get the sum of these values, you will see a value like -90. But let's say I have the exact area of an eyebrow, an eye. So the eyebrow is black, just for simplification, dark, and under it, the eyelids are bright. So let's do the same multiplication. -1 times 0, plus -1 times 0, -1 times 0, plus 1 times 200, plus 1 times 200, plus 1 times 200, it's 600. So if the sum of this multiplication is over a threshold, which we will find out that threshold from experience, then we will be able to say, I have probably found an eye-like area. And what I do is I take the image, I take it to different resolutions, and apply different filter sizes. Now, this is for simplification, a very small filter, 3 by 2 or 2 by 3. It's a very, very small one. We can take bigger ones, and we can do different resolutions of the image, and then we will feed that to our model. So the integral images idea is another way of doing this multiplication. I will talk about integral images later, but the idea is once calculate all the values in a matrix and then do this multiplication. It's a very, very simple idea. And it makes it times faster. Instead of doing all these multiplications every time, what I do is I calculate this bit, the sum of it once, and I calculate the sum of it once, and then I said minus this plus this. So instead of having these different multiplications, I have just one run. And it makes things several times faster. So I will talk about it later in more detail. So the general idea is to find areas that have a high response to these filters. So this is the way face detection works. Let's have an example. So in MATLAB, it is just 2 lines of code, right? What you do, forgetting about reading the image and printing it, this is these 2 lines that are important. I call it my face detector, you can call it whatever you like, is vision.cascadeObjectDetector, which is a sort of classifier. And then I say classification model is frontal face card. If you leave these 2 blank, this is the default. So if you leave these 2 blank, just say vision.cascadeObjectDetector, it will automatically work. You don't need to add any parameters. But this function has more parameters. You can say find nose, you can say find different parts of the face, eye1, eye2, and things like that. And then the next item is bbox equals to my face detector A, which is my input image. And it automatically finds all the faces. Let's see if it works. So I'm going to open MATLAB. I'm doing your coursework now. So I find an image which I am interested in. So by the way, I uploaded all the images online. I will talk about it by the end of the lecture. So I have an image which is interesting to me. Let's say 8244. Right? This is an image. This is one of the ones we took last week. So you all look good. And what I want to do is I want to detect faces in this image. Yep, happy? So it is 8244. I have already written this code, 8244. So I read the image. And I say my face detector is vision.cascadeObjectDetector. I can leave this bit blank if I don't want it. I don't have to have this bit now. And then I say bbox is my face detector A, which is my image. And then insert annotations just to show the items. Then press run. Let's see how it works. So, yeah, see, your coursework is easy. So the first step is to detect faces, right? Let's see how it worked. So it has detected almost everyone here, missing this face because it's like half visible. This one, and so it has missed a few faces, but other than that, it's all good. So let's zoom out. So in this area, it's missing a few faces. So let's zoom in to that area and see what happens. So what I'm going to do is I'm going to crop that and make it this bit and do this bit again. So it is 8244-2. So I'm going to comment this line and run this. Okay, it detected these faces as well. So sometimes resolution matters. Instead of generally reducing the resolution of your image, if there are too many faces in it, you can crop different parts and then feed them separately to your model. So it's very simple, right? It's just detecting almost all of the faces. Let's do another one. This is a panoramic image that I took because you didn't fit in one picture.
So why would increasing the resolution help with that?
Because they have a limit on the resolution. These models, they don't go to too much detail. They have a hierarchy and it has a size. So if you want to go further, you have to give it a bigger image.
Okay. So would it be more likely that they cross that threshold?
Yeah.
Okay.
But as in this one, you see almost all the faces are detected, but this bit is also detected as a face, or this bit is detected as a face. So these models are not 100% perfect, and the reason is there might have been some pattern on a clothes that might have looked like a face. So this model doesn't know a human. It's not looking at a human. It's just looking at things that satisfy that hair-like features. So you have to be careful with false positives as well. So you see, just 2-3 lines of code, and most of your coursework is done. Not really. Okay, so this is another thing that I wanted to show you. This is a very good link in MATLAB, in MathWorks website. If I can bring it over. So this is computer vision system toolbox. And on this one, you see a lot of videos and webinars and example codes for different tasks in MATLAB. So this is a very good link for deep learning. This is, as you can see, it's a segmentation. It's telling you where the objects are. You can do object detection and recognition. You can do camera calibration, stereo vision when you have 2 cameras and you want to estimate depths from it. You have 3D point cloud processing. You have object tracking and motion tracking estimation. We will talk about these things in lecture 8 and 9. Stereo vision, camera calibration, motion estimation. These things will be lectures 8 and 9. Well, we will have one of the best lecturers, Greg, will be with us for lectures 8 and 9. So he has kindly accepted to talk about these things. So we have some algorithms, some toolboxes in MATLAB, which is, for example, one of them is Coder, and you can translate your code which has been in MATLAB to C++ or to other languages. It's not perfect, but it works to a very good extent. It has some limitations. You cannot translate some functions which are fundamentally different in MATLAB, but most of the work you have, you can just go to Coder, run, and it converts it from MATLAB code to C++. So there are a lot of resources that you can use. There are a list of functions for computer vision. There is a community and support. If you have a question, you ask, and within 2 years, you will get an answer. So they are, but generally, it's a very good page. So I suggest having a look at it. All right. So this is the example that we just ran, and so how easy it is to detect faces. So for your coursework, what you can do is this code is giving you all the B boxes. B box is a bounding box around each face. So it gives you the coordinates, the width and height of it, and then you can extract that bit and use it for training your model. So you can see how easy it is to get faces from images. But if you wanted to do it yourself, it would be a long work. Yeah, like. And so the false positive and true negative example, it's sometimes if somebody doesn't have cancer and you tell them you have cancer, or if somebody has cancer and you tell them you don't have cancer, which is more damaging. So you have to see in what context you are working, and sometimes you fine-tune your model in a way that you in order not to give any false negatives, you want to give more false positives. Usually there is a threshold. Let's see it in an example. So in the previous model that we discussed, I gave the parameter frontal face cart. This is a sort of feature that it is using, but I want to see what else I can use. So what I do is I copy this function name, I open a page and paste it, and say MATLAB. It opens the page for that for me, and now I have a full help page for that. I could also, while this is loading, I could also type help the function name that I'm looking for example, help IM resize. So it gives me some definitions of how this function works, what parameters you need to use on this function, but I like it on HTML better. It looks a bit nicer. So what you can do is you can open this page and it shows you a description of the function, the papers it is citing, where these models are coming from, and different ways to call this. It shows you the input arguments, output arguments, what the B-box means. It shows you what each individual value in it, x, y, width, and height. So it's showing you 4 parameters, x and y, top left, and then the width and height of the box, and so on. So it also tells you for older versions you could do this, blah, blah, and it tells you that the classification model can be different. So let's open this bit. And now we see we could, instead of using frontal face cart, we could use LBP, which we will learn what it is today. We could go with upper body. We could go with eye pair big, eye pair small. There is a definition what they mean, what is the image size used to train the model, and stuff like that. Let's do, for example, nose. So I copy nose, come back to this function, and change it to nose. So let's see how many noses we have. Probably more than. So it's now looking for the knees in the. So you can see now there are a lot more false positives, and there are still false negatives as well. So on.
So does that mean it's not picking up the thing below the thing that's the eyes, but it's looking for a different pattern?
It is looking for the brighter area in the middle of 2 darker areas, but probably this bit, it's a big box, which is detected. Maybe there is a dark area here, there is a dark area here, and there is a bright area here.
Because it's not usually a nose without a face.
Yeah. So it's just looking for a box like that. So you see this is a bright area in the middle of 2 darker areas. So it's stupid. Yeah. Let's see. So this is the different classification models. Oh, there is min size and max size. So you can choose the sizes of the box that you want, how big it could be. So if you're looking at group photos, the sizes of faces are very different with when you're looking at individual photos. In individual photos, your face is taking, like, I would say, if the images are 4,000 by 3,000, your face is probably 1,000 by 2,000 of it. It's a very big portion of that image. But for the group photos, those faces in the back are maybe like 50 by 50. So you have to play with these parameters. This is the scale factor and the merge threshold, and using region of interest and things like that. So you can go through the help, read what functions do. And for those of you who are doing Python, there are enough support for OpenCV documentation, different libraries in Python which you can use, and all of them have some similar support pages. You can find the functions, see how they work. Okay, so I just changed this to what it was.
Question?
Yep.
Can you combine 2 filters, like first do face detection and then do detection of the
Yes, very good question. This is what you can do for your coursework. So once, for some images, you see eyes, but it's detecting a lot of false positives, then you can run a nose later to see, now you combine these two. If a region is around the eye and it is around the nose, then it is probably on a face. If it is not, if you only see a nose and you don't see an eye, it's most probably not a face. But this option, this frontal face, is already considering that. Okay. It's a more complicated version. It's a more comprehensive version. It has all of these ratios. So if it sees an eye, like in this one, you didn't see that nose in the lower corner of the image because it couldn't find the eyes around it in an area where they should have been. All right. So this is used a lot, for example, in Google Maps. But as you can see, there are false positives. This is detected as a face. This is a face, but we didn't want to blur it, but it doesn't understand. It just sees a face. Doesn't know it's a painting or it's not a problem. Like the KFC, the colonel, here is now blurred as well, which I don't think he would mind not being blurred. So there are problems. And for undergrads, one part of their coursework was to do funny things with faces. So you can see this is a funny thing, for example, but not really funny. So this is like 4 years ago when the first group of students were taking computer vision. This is Greg. The face will be revealed in lecture 8. But you have seen his face in lab instructions. So the faces are all blurred. And how do we do blurring? How do I blur the face? So I extracted the boxes, right? I know the starting point, and I know the widths and the height of them. So I know a small part. I have that box. So now I blur it. How do I blur it? We will learn today. So this is things you can do. For making it fun, you can do fun stuff instead of just blurring. So depending on the job that we have at hand, we will use different sources of or sorts of features. For example, for face detection, as you could see, hair-like features are almost enough. In most cases, they work. Some students took a further step last year, and for face detection step, they downloaded face data sets online. They trained a deep neural network, like it's called the YOLO. You only look once, not live once. And there are other versions for object detection like fast RCNN, faster RCNN, mask RCNN, which are models that track, find or detect objects in an image. And they use those to detect faces. It's much more accurate than these hair-like features. As you saw, this is from 2001, 17 years ago, 18 years ago now. But deep learning models are more up-to-date, and they are even more and more accurate. And they are more fine-tuned to different variations. They deal with occlusion better, they deal with different skin tones better, they deal with glasses, hats, and things like that better. So you can try that, but you don't have to.
Just a question, do the properties of the image matter? So if you change somehow the parameters of brightness, for instance, does it have an effect?
It may. It depends on how much you change them. It may have an effect, yes. So assume we have these samples and we want to, say, find people who have long hair. So what we would look for is hair length. So if you have that, then problem is solved. But if you want to say what is their facial expression, this is also a very interesting and challenging and still active research area. Companies are very interested in your smile, and they want to see you are happy. For example, some cameras, they also, you have seen them, they have a smile detector. So you open the camera and look at it and smile, and it detects your smile and then takes a photo. So in order to do that, you need to be able to detect facial expressions. So you need more complex ratios between facial parts such as mouth, teeth, eyes, and so on. So depending on the job at hand, you will be looking for different sources of features. Well, if you are going to say separate photos of men from women, what would you look for? Long hair? Could be helpful, but not necessarily. We have men who have long hair, we have women who have short hair. Mustache and beard, most of the times. Baldness, almost most of the times, but these are not comprehensive. This could be like funny images people have made and so on. So now let's go to a classical computer vision problem. Image classification. Generally, many of you have approached for thesis ideas. You are looking for doing something brilliant in computer vision, and most of your ideas are startup ideas. They are not a thesis idea. You want to come up with something that is doable during a thesis period, not just something that you can sell it immediately next week. Some of the ideas are too complex, and they need a lot of work. They need a group, actually, to work with different aspects of it. But when it comes to computer vision, most of the works are broken down into a few small parts. They are either image classification, where you have images of cats and images of dogs, and you want to separate them. And once your model sees an unseen image, you show it a new image of a cat which it has never seen before. You want your model to be able to say this is a cat or a dog, right? So this is classification. So the models are the same, and now they apply to thousands of different applications. You can do this on cancer, non-cancer. You can do this on vessel, non-vessel. You can do this on human, not human. You can do this on, you see? So the idea, and you can do it in different, multiple classes. Like, is this an image of a dog, a cat, a zebra, or a giraffe, for example? So this is multi-class classification, or you have binary classification. It's either one line or a few lines. We'll see that. So this is one major side in computer vision. The other side is image segmentation. You have an image, and you want to segment parts in it. This is a wall. This is a person. This is a floor. This is a door. This is a projector. This is an LCD. So you just want to find parts and color them differently. This is a coin. This is not a coin. And you want to find the area, exact area of that item, rather than just saying this area contains a coin. Say this is the coin. This exact bounding box is the coin. So that is segmentation. You have other aspects that are more novel, like super resolution, for example. You have images that have low resolution, and you want a high quality image built from them. So if you have a high quality image, it's very easy to make it low quality. But if you have a low quality and you want to make it high quality, it wasn't possible until recently, which we have tons of images. Our models can learn from them, and then they can find the ways to improve the quality of images and make them better resolution or better quality. We have registration, which is also very interesting and important. You have two images taken, for example, during surgery or before surgery. Before surgery, the patient is awake, steady, sits behind your machine for 20 minutes. You have time. You take hundreds of images, whichever you like. Okay, this is the best image I got from your lungs. I'm happy. You can leave the room. But during the surgery, you don't have that luxury. There is, the camera has to create real-time images as the doctor is doing the surgery, and the images are low quality, and there is blood, and there is fluid around, and it's like occlusions, the tools are in, the doctor is doing parts of the whatever it is, the tumor removed. So what you need is something called registration, to put that high quality image on top of this low quality image, so that the doctor sees where he is in more detail, the detail that you have from before surgery. So there are different areas that you can work in computer vision, but as I said, there are limited numbers. It's not like a lot of different things, and mainly the applications are different. You can work on stereo images, you can work on videos, you can work on surveillance, for example, videos, and things like that. So you have videos, images, different sources of images, registration from these different formats, classification, and segmentation. So we will get to that. So image classification is one of the classical computer vision problems. It has a lot of applications, and as I mentioned, my PhD was basically trying to understand how human brain works, simulate it on a data set of, at the time I was working on Caltech 101. It was a data set, some people collected 101 categories of different objects, like animals, mobile phones, things like that. Everything was from internet. And I had to write a program that could separate these classes. And when it sees an unseen image, it says, okay, this is a mobile phone, this is a zebra, this is a giraffe, this is what. And my model was trying to understand how brain works and to come up with ways to do that. So image classification is basically you have two different images and you want to be able to tell the difference between them. The way machine learning usually works is you have a lot of training images. You have 1,000 different images of, in this case, sea bass and salmon. You have 1,000 sea bass, you have 1,000 salmon. So you want to find features that make you be able to differentiate between sea bass and salmon. You don't want to use the actual image. If you have features that you can extract from the image, create a feature vector, and then find a line between those, you have a very easier job. Let's see how it works, how we can create a feature vector. So what features are there? Let's say I have these images. Could be the length of the fish, the lightness, the width, number and shape of fins, position of the mouse. I could look at several different sources that can help me differentiate between these two sort of fish and understand them. Let's say the size of the fish. Usually sea bass is longer than a salmon, but is this enough? If I see a fish that is 500 pixels in my image and another one which is 200 pixels, is it enough to say this is probably a salmon or sea bass? No, maybe it was a small sea bass or a small or big salmon. So an easier way would be the ratio of the width and length. It might be enough. If one of them is 500 pixels and the width is 200 pixels, this is probably a thinner fish. And if the other one is like 200 by 200, this is probably more squarish fish and it's more probable to be a sea bass, for example. So what I do, again, you don't do this in computer vision, but for understanding what classification is, I calculate the length and width of this fish. And what I do is I create a feature vector, or in this example, calculate the lightness and width. So usually in this example, we say sea bass is lighter, or the other way around, salmon is lighter. So I have a different value. I have the lightness and I have a width. So what I do is I create a feature vector. I say the fish that I saw has a lightness of 100 and a width of 500. The other fish that I saw has a lightness of 50 and so what I am basically doing for simplicity, I'm just making it into 2 dimensions. I say this is lightness or width, because I said width, whatever. And here we say length. So fish number 1, let's say this is 1 to 200, and this is 1 to 300, right? Fish number 1 is a salmon and it's here. Fish number 2 is a salmon and it's here. Fish number 3 is a salmon and so on. So I have 10 different salmons. And what I have, this is a sea bass. So I have converted those images into features, in this case 2 dimensions. Classification means finding an optimal line here. That's the whole idea of classification in machine learning. So you find a line that separates your data. And this line, the way you find it, it depends on the method you're working. Neural networks, support vector machines, cascading classifiers, and so on. So basically you're finding a line. That's the way it is. There are a lot of things to consider. If I have a salmon here, what should I do? Should I just ignore it? Then this will reduce my performance. Or should I change my line into something like this, which is not a good idea most of the times? Or should I change the dimensionality of my input? Add a third vector. Say, I don't know, number of fins or whatever. So we can add more features, something that would make it easier to separate the features, the items that you have. So this is a very, very simple classification thing. But if I have a lot of points that are overlapping, then my model is not good. These two parameters are not going to work. I have to come up with something better. My classification accuracy is like 30%. Nobody's going to pay me for that, right? So I have to come up with a better model. I have to find better features. So this is the idea of classification. Finding the optimal line. Depending on the job that you have at hand, you will need different sources of features. If I have a constrained area, and I have a camera which I know exactly where it is, and I have an environment that I have control over it, and I have calibrated my camera, which means I know each pixel in my camera is how many centimeters in the real environment, because the camera is fixed, I know all the statistics of the environment, then I can measure the width and height of my object. Otherwise, it's not that easy to just find the width and height in centimeters. You can find it in pixels always, but in centimeters to translate it, it's not that easy. Depending on the job that I have, I will need different sources of features. If you are looking at fingerprints, for example, you have a constrained area. You know all of your images are collected with one of those machines, and you do have control over your area. You know what a fingertip size is, and you can draw features from them which are going to help you differentiate. But if the environment is less controlled, like you have a camera which is like on a police car, it goes on different positions on the road, it has shaking, it has cars approaching at different distances, so it's not that easy. You have to come up with better features to detect the items that you're looking for. But if you have a stationary camera, fixed location, you have lines on the road, you know when the car is entering and when the car is leaving, and you have the measurements, you know from line 1 to line 10, it is 30 meters. So if this car entered on line 1 at time 005 and left line 5 at 0052, then this car was driving at 67 miles an hour. And you know in this area it was 50 miles an hour. So you automatically trigger a camera, take a picture, and send a fine. This is computer vision based. You have other methods. You can do laser points. Like you send a signal to the car and immediately send another signal again. For the time that it takes for the two signals to come back, you will calculate the difference and you will calculate the speed of the car. And if the speed is over a limit, then you trigger a camera and the photo is taken, a flash or the photo is taken. So this is a very applicable thing. If you are looking for facial features, depending on whether you're using deep learning or you're using conventional computer methods, you look at different things. Deep learning is about big data. In deep learning, usually, it's easiest to have thousands of images for different items. You have 1,000 smiling faces, you have 1,000 angry faces, you have 1,000 sad faces. So you train the model and it then automatically extracts features. And once you give it an unseen image, it tells you who is sad, who is happy. But in traditional computer vision, you do detect eyes, you find where they are, you detect the lips, you calculate the ratios between them, you see if the tips of the mouth are like this or like that, then whether it's smiling or sad or angry, you find the correlations between the eye and so on. Well, what we need is an ideal feature detector, a feature that is robust, it's reliable. And what does it mean? For example, if I have a corner like this, and I can detect it here, and then I have this same corner, but in higher size, but my filter is still the same size, then I won't be able to detect it. This is the same hand in different lighting conditions. So you can see how different it is. So color is probably not a useful characteristic in this outdoor environment. You have, if you're trying to detect faces, there are a lot of occlusions, there are a lot of noise, background, and different lighting conditions. So a good feature is something that is it's insensitive or is tolerable to changes in scale, lighting, perspective imaging, partial occlusion, and things like that. Today, after a quick break, we will talk about edge detection, finding the edges in an image. And next week, no, the week after next week, we will talk about more advanced feature extraction methods. We will see how we can actually find something that works here. All right, have a break. See you in about 10 minutes. Hi.
Sorry for that.
No worries.
I tried to get in touch with you last week. I missed you unfortunately yesterday evening. Last week, lecture. My email just received. I haven't heard anything back.
Yeah. I am going to make an announcement on that today. After the lecture, I'm going to reply to all those who have shown interest to be our students. The news is, unfortunately, the university is no longer giving the visiting lecturers the quota of supervision that they had. So previously, the class was like several students, but this year they have a very small number, which is already taken. But I will announce this later after the lecture, and I will advise what can be done. I would be happy personally to take more students, but the school at the moment is hesitant on this. So I will have a brief discussion with you, and like after the lecture, I'm going to go on to all of those lectures that have a group discussion about that. That's why I didn't reply to your email.
Is there anyone in particular who you feel the fact?
Yeah, that's what I'm going to say. Cheers. Hi.
You're right. I'm going to have to skip the second half. We've got some urgent work to do, so I'll catch up.
No worries. All right.
I did send you an email. Apologies why I haven't got back to you. But
No
it's
worries.
been
I was
hectic
just
week.
explaining to him as well. There has been, unfortunately, some changes policy this year, and they are no longer giving visiting lecturers the 40 days for the student supervision. So last year I could supervise several students, but this year they have made it less because they have employed some other lecturers internally, and they want to give them something to do. So I am going to say to everyone who has sent, I have taken a few which approached me first, and other than that, I'm going to, unfortunately at this moment it's a point race. I would love to personally take more students, but as of current circumstances, it seems that I won't be able to unless there is too much demand for computer vision and they think that they have to assign more students. I would be happy to take. Other than that, at this moment, I'm afraid if it doesn't change.
I think I heard you say to him you're going to send out some alternative lectures.
I'm going to, so what they have said is basically to students to approach Andre and looking at this last minute, it's Andre and Lorenzo. Yeah, to discuss what should be done. Most probably they will ask you to do something other than computer vision if they don't have computer vision supervisors. But if at any point it is decided that they need my support, I will be there.
Okay, well, appreciate it. We're updating you.
Cheers.
For your what do you
I use, so my project is different. Some parts of it which are trials and all these things work is not because it's really straightforward. But when it comes to implementation, I'm using Python.
Because I think that he came and gave us data we did ask him how is the technical done. He said, so I was thinking how is this Python?
possible to not do this. Most of the work that is done is R&D. And R&D is really university, and university is still using it. So because MATLAB is very expensive, so if you want to use it for theory, I want to sell a product from MATLAB. So people who use MATLAB basically doing academic research. If I want to produce a product, then they go with
So if I learn all these functions from here,
all of these functions are there. Different parameters, different ways of implementation, but all of these functions are there. It might be different. Like there are some functions that are easier in Python, there are some functions that are easier in Python. So we have to see everything, but it's the same.
Sometimes the language I see are more. So if we're doing MATLAB and changing it, that's is that not
It's
more
not
way?
that good. So it works to some extent, but it's not it won't be like good to go. We will definitely need to play with it a lot.
So the better option would be just go straight to the language. And one more question is like, you know, if you look at the power feature from I'm sure other people are on better algorithms as well. It's just that.
No, it's not an optimal one. As I said, deep learning models are not optimal. But this is a very simple one.
You mentioned that for
So, you need to install and SDK, software development. If you go to NVIDIA website, I'm using Python. So MATLAB automatically has it. Once you install those, MATLAB is automatically set up. So what you need to do is you need to write GPU device, and then it shows you whether you are using your GPU device or not. You can run that command. You do need to. It shows you if it is installed or not, but type in GPU device. GPU, big device, camel,
Just be sure what this is. So basically I was pictures of the class and single pictures of people with numbers, right? Your task is to recognize single person or
I will give you an image and you will tell me which person is what number. So all of them have a number. So you have different people, each of them has a number, and then you just assign each number to a specific, each person to a specific number. So like the group photo that you saw, I found faces, but your job is to get that face and put the number on top of it. So face 1, face 5, face 8, face 23.
it's not related to recognizing the number on the plate, right?
You should also be, if you're a master's student, you should also be able to recognize the number. And that's a different software.
So from a single image of the person with the number, in that case I should recognize the number. And then apply it.
I will explain a bit more throughout this, but if you read the coursework description, it says everything. And the idea is you have a master's student, you have two tasks. One is to detect that number, and this is two actually, and one is to detect faces that go with that number. So it's two different things. One is face recognition, one is optical character recognition.
Some of the tools are really as we just said. And they're covering some all the details of this kind of stuff. But I did some Python.
Great. Python is more encouraged than the rest. I'm happy for you to use the Examine it. So I suggest one, because if it's two platforms, then they have to be tested.
All right. So let's get to kernel-based image filtering, which is what we already saw with Viola-Jones filters. The way it works, like Harlike filters, is you have a filter, like what we saw, and instead of just applying it on one portion, which we didn't, we apply it all over the image, like we did, and find the points that look similar to the object that we want. So how does this work? For Viola-Jones, what we had was a box like this, which had, for example, some negative values and some positive values. So we want to detect edges. How can we do this? We will find a kernel that does the same thing for us, convolve it on the image, and see what it looks like. So there are different kernel-based images. One of them, for example, if you have an original image, you can blur it, less details. You can sharpen it, more details, and usually a bit more noise. And you can detect the edges in that image. So these models usually combine pixels from the original image to produce an output pixel. So linear filtering refers to looking at a neighborhood in an image, using the values in that neighborhood, which we can define the size of it, to create a new value in the output image. So it's a mapping from input image to output image, which is usually a weighted sum or weighted combination of these weights in that neighborhood. Let's look at a simple example. So this is the equation. You have a kernel, and you have a kernel size, and you have a point. And for each point in the output image, you convolve or multiply that kernel into that image element-wise and calculate the output. So let's look at this example. Let's say this is a patch in my image, and this is my kernel. How do I do it? I just say 1 times 22 plus 0 times 23 plus 1 times 24 plus 0 times 27, and so on. So I did 9 multiplications and additions, 8 of them, and then I come up with a value, 168. So this is this kernel multiplied into this image, and it gives me one value here in the middle. But as you can see, I cannot do this for the borders. So if I have a big image, this is just a very tiny example. Fortunately, these markers are almost dying. So if I have a big image, let's say my image is this big. Say it's an 8 by 8. And I have a kernel which is 3 by 3. So if I take this mask and apply it here, I will lose the borders. This is the first value I get, right? I take the same mask, apply it on the next one, right? I get this value. And do the same. So these are the values that I can fill in. Right? I lose the borders, just 1 pixel. 1 pixel, 1 pixel. That's not that important generally. If I have an image which is 500 by, I would say maybe 600, for example, then just 1 pixel here and there doesn't really make a difference. But we have ways to go around that as well. Yes, yes, yes. So if I have the image like that, the kernel like that, and this is just one small box, a 3 by 3, multiplying that, I get this area. So just again, be careful. One of the good things about Moodle is that you have that discussion forum. I look at the questions, and thank you for those who ask, and thank you for those who answer questions. If a question is unanswered, I will answer as well. But so far, there hasn't been much need to my answering, so thank you to those who answered. So one of the problems was someone had exceeded the numbers on the range that was acceptable. So we have the same problem here again. So if I multiply this mask or this kernel on this image, which is unsigned integer, the value would be actually 368, but what I will see is 255, because this is the max that I can show. So generally try to convert your images into double, do your whatever work you want to do, and if you have to, then convert it back to unsigned integer. Because if you don't do that, you will lose a lot of information. You will see funny colors, funny images, which are not supposed to be there. You don't want those. So what happens is if you exceed those limits, you have to normalize them. But if you cannot, you have exceeded that limit, everything that has been over 255 is back to 255, so you see a lot of white, right? The other question was about CUDA. I will talk about it at the end of the lecture. These are the things that I want to talk about. So here, just have that in mind. So now let's do a bit another example. I want you to calculate this value for me, please. Don't cheat. How do you do that? This value. I just want you to feel it, so that once you go to programming, you understand what you're doing. How much is this, the value in this box? It's a very, very simple thing to do. So what I need to do is say, yeah? Yeah. So 1 times 23. So what I need to do is shift that box. So you see, I'm shifting my box 1 pixel. This is called a stride. My stride is 1. You will see that in deep learning a lot. So stride 1, and I have padding 0, which is the corners, this area around here. I'm just forgetting about them. I'm not adding any padding. So if I want to add values here, I can by adding values here. So if I want these values, so what I do in the original image, I add, for example, zeros. Or I add this value, put it here. So I add a padding and repeat these values, whether, different models, right? So this is padding, 0. I'm not adding any zeros around here. And now I'm shifting my box to 1 pixel. So it's a stride 1. And I have this value. And the rest, this one. Again, shift this red box once. It's 1 times 24 plus 0 times 25 plus 1 times 26, and so on. Okay, got it? So this is the way we apply a kernel to an image. We start from a corner, and we keep doing it. Sometimes we keep a higher stride, like stride 2, stride 3. We don't want to do all of them. We want to make it a bit more sparse. Sometimes we add padding, sometimes we don't. Sometimes we have to. You will see that in deep learning. Sometimes because you want your layers, the sizes of the layers to make sense for the convolutions that you have to add padding so that you can multiply them. Anyway, what we have is these values, and this area is 0. As discussed, you can pad it. So these are the equations. What we did is cross-correlation, which is the same as convolution if the kernel is symmetric. There is a discussion on what the difference between these two are, but we usually use convolution. So it's just if the kernel is symmetric, cross correlation and convolution are the same. So we use convolution a lot. So let's do another example. I have an input image, and I have a kernel, which is all ones divided by 9. What is your feeling about this filter? What is it doing? It's close to summing, but I have 1 over 9. So if you have 9 values, add them and divide them by 9. What are you doing? Yeah, averaging. Yeah, finding the mean. So what I am doing here with this filter is I'm basically in each 3 by 3 region, if this is my region, so on each 3 by 3 region, I'm adding all the values, divided by 9, and put it where it belongs. So each pixel is the average of its 9 neighbors. What would it do? It would blur the image, right? Because I'm putting the average of those. So how would it work? If I have a value 0, 0, 0, 0, 200, 0, 0, 0, 0, what I will get is 200 over 9, let's say 20, making it simple. So everything will become 20. So it's averaging it. It's killing that one pixel that is probably noise. Because it doesn't make sense to have a 200 between 9, 8 zeros. It's most probably a noise of the camera or whatever. So I'm averaging it. I'm eliminating that noise. Have you seen noise reductions? On some cameras they have it. What they do is they pass this filter, or one of the variants of this filter. So if I multiply this kernel, which is averaging on an input image, I get an output image which is the average. But what if I make it bigger? If I make this, instead of 3 by 3 kernel, if I make it a 5 by 5, so I would be averaging even more. 6 by 6, for example. Okay? I'm averaging it even more, or 7 by 7. Normally these numbers are odd. 3 by 3, 5 by 5, 7 by 7.
Do you also try as your averaging out?
Yeah, you just go through the whole image, like what we discussed, one row at a time, so that the whole image is like that. In MATLAB, it's very simple to do it. You just call IM filter. So what you do is you create a kernel, like look at the code here. I say I is double, read that success kit image, resize it, because that image is maybe too big. I can resize it, make it smaller, faster, depending on what I want to do. You can skip this line. And then show the original image, and then create a kernel. I say k equals to 1 over 9 times 1s, 3, and 3. So 1s, 3, and 3 generates a 3 by 3 matrix, which is all 1s. And then I'm multiplying it by 1 over 9. Right? And then I say IM filter I and K. So it's blurring it. So if I want my image to be even more blurred, I can use a bigger box. Instead of saying 1s, 3, 3, I say 1s, 9, 9. And then make sure you divide it by 9 by 81, for example. Because then you are averaging 81 values. So you have to divide it by 81. Right? So let's see how it works. This is a little bit of blurring. This is more blurring, because now I am taking a bigger neighborhood and getting the average. And this is even more blurred. So if you make your size of the filter bigger, average a bigger area, you're blurring your image. So undergrad's coursework done. Let's go to postgrad. So another part here, as I discussed, is you can add padding to your images. So for the input image, you can add a line, a row and column of zeros, for example. You can call an image intensity around it. You can use the symmetric or replicate for adding padding, so that these values will also be calculated. if you don't do that, you usually will have your border areas of 0, black, around your images if you don't add padding. So you can crop them, or if you have to keep the size as the same, then you have padding. So for padding, what you do is you have an input image. If you don't do padding, as you remember, the first value that we could calculate was here, right? We couldn't do anything on the borders. But if you want to have values for borders, what you can do is add an imaginary row and column and row around the image and put values in it. What values? You can put zeros. Or you can just replicate the nearest pixel value to it, or you can do the symmetric. So if you do that, like you will have 28 here, 22, 23, 24. Or if you do this replicate, you will have 27, 22, 22, 22, 23. Or you can have zeros. Yeah?
If you're working with like a 5 grid, how does the boundary work? Like, is it a padding of 2 or?
Yeah. If your kernel is 3 by 3, you will have 1 padding. If it is bigger, if you want these values again to have value, you have to make it more, you have to make it bigger, so you will have more padding. You will have, in this case, you will have 4 padding, I think, yeah. So if you want the sizes be exactly the same, you must do padding. But if you don't care, that's why I said in convolutional neural networks you do need padding, because you have to have a same size and you have to make sense to the next layer. That's why padding is important. But if you're just doing one image, you can just forget about 1 pixel here and there.
If you have like 5 filters or 10 filters in a row, just the padding you would read.
You have to customize it, yeah. So it depends on the size of the filter. In lecture 7, I will explain the equation between padding, stride, and the input size and output size when it comes to that. Yeah.
Does the padding have to be an odd number, or can it be 4 by 4?
No, it can be any number. Depends on the filter size. You can have filters of different sizes. So this is what we do with padding. As I said in lecture 7, when we go to where we actually need padding, because for these images you don't care about the column and row of black, but in deep learning models, when you have one layer and that layer's dimensions has to make sense to the next layer dimensions, you have to add padding accordingly. So there are equations for that. The other way of doing filtering is Gaussian filtering. Gaussian is also another blurring. What you can do is you can write the Gaussian equation. You have a sigma value, and which is the amount of blurring you want. The more blurred, and you have the grid size, the size that you want. In MATLAB, we just called f special Gaussian 5, 1, for example. This is sigma 1, and this is a size of 5 by 5. So it generates something like this, and then multiplies it all over the image. So this is your kernel. Now you have to IM filter it, right? So this is another way to create Gaussian filter. So now I want to sharpen my image. What do I do? This is a filter that sharpens the images. It makes edges more pronounced. So far we were adding values of the neighbors together and averaging. Now we are deducting the values of the neighbors from the center point. So by deducting those values, I put -1s around here. I am deducting the values. I am sharpening the image, right? So this is another kernel. So as you can see, a sharpening kernel is just multiplying it 6 times and then deducting 5 times. So I am eliminating, so I'm taking that image, multiplying this central point 6 times, and deducting the neighboring points, including itself, 5 times. So I have original image minus, this is the blurred image. This is another way of doing blurred image. So I'm taking the original, making these central values more higher, and then deducting the surrounding ones. So it's original minus blurred. So I'm extracting one blurred version from that image so that I get a sharpened version. So if generally for blurring images, you go with the rule of thumb of n equals roughly 3 times sigma, which is n is the size of your filter. So here I have a Gaussian filtered image with sigma 1, with sigma 3, and with sigma 5. So you see the higher the sigma, the more blurring you get. It's very simple. You can blur your images. And it keeps the general structure of the image, but it makes it less sharp. Yep?
How do you know if the blurring is going to be safe in a situation where you're trying to hide someone's identity?
What do you mean by safe?
That you couldn't use neural nets or relearn the original signal.
I'm not following. Is it for like identity reasons? You don't want to be...
For example, identity reasons. So removing the blurring and going back to the original image, is that possible?
So you want to remove blurring or you want to add blurring?
I want to remove blurring so I can look at what the original image was.
So, yeah, you can just do this, sharpening filters.
Yeah. So, I mean, in the situation where people have blurred out people's faces.
Oh, you won't get that. You won't. If you see this image, no matter how many times you apply this, you won't see this. It's not going to happen. It's not a linear trans. It won't happen, because if I have 5, like say I have these values, and I add them, I get a 9. So if I want to go back and eliminate some numbers that the sum is 9, it could be anything. It could be 6, 0, 0, 0, 0, 0, 0, 0, 3. So you won't get that original signal. You won't be able to do that. Otherwise, all of those images that are blurred on Google, people would just unblur them and see who was there. It won't happen. Because you're destroying a signal. You can't reconstruct it. So, edge detection. Now we are a bit more familiar with blurring and sharpening images. Now we want to see how we can detect edges, corners from images. The idea of edge is very simple. So for each pixel, go through the image matrix pixel by pixel for each pixel. Analyze each of the 8 pixels surrounding it. So I have a 3 by 3 area here. I analyze the 8 around it. If they are bigger than this value, it says record the value of the darkest pixel. So I record, let's make it a bit more reasonable, 10, 20, 30, 40, 50, 60, 70. And I have another 10. Make this 15. So for areas around it, I find the value darkest around it is 15, and then I find the lightest around it is 100. I deduct 100 minus 15, I come up to 85. 85 is more than my threshold, so I say probably there is a border here. These two are very different. So I'm probably finding an edge. Maybe one was 0, one was 255. There is a good chance. But we don't go with that big a gap. Like I would say maybe 50, it is less. The difference between them is probably an edge. But it is not easy to do that. I want a way to do it with a mask, with a kernel, to just run it through the image. How do I do that? You have to come up with it. It's you decide. If your images are, everything is too bright, and then you have something that is a slightly darker, or if everything is too bright and everything is too dark, it differs. It's manual. But if you look at this image, and I look at the values in a row, this is what the intensities are. So this is the raw values, and this is my x dimension, and this is the brightness from 0 to 255, and my image is, say, 350 pixels wide, right? So if I look at these values from here, this is the brightness. So I see different values, but at this point is that I see something that was bright is now super dark, right? It's dark again and it's bright again. So as you can see on this line, I'm passing through the eye. So there is a very big difference here. But this difference, the way you can calculate it, as you remember, is to take a derivative. So you can take a derivative here, and if the derivative, the value is higher or lower than a threshold, you can decide whether it's an edge or not. What's happening? Some people are fighting? No. Okay. Let's wait for her. Any chevalier to go and save her? No? Thank you. Yeah. All right. So you can see there is a big change from intensities which are bright to intensities that are very dark and back. So this point is most likely a point of an edge which we are passing. If I take the derivative here, I see a large negative value. So the way is to find derivatives that have a large value. If it is a large negative value, it's probably going from white to black, and the other way around. If it is a large positive value, then I'm coming from white to black to white. So the way to do this is you can do estimate this using finite differences. Don't worry about the math. The final idea is the way to do it is you get the pixel value to the right minus pixel value to the left over 2. So if this value is higher than a threshold, you have an edge, right? So you get the value to the right. I have a pixel here. I get the value to the right. I get the value to the left. 40 minus 30 is 10. Divided by 2 is 5. Nah, probably I don't see a big difference here. I said this is not an edge. But if I have here the value to the right, 20 minus 100 is minus 80 over 2 minus 40. It's more likely to have an edge here, right? So how do I do that? Very, very simple. I just say 1 over 2 times minus 1, 0, plus 1. Right? The value to the left, the value to the right, minus value to the left divided by 2. So this is my edge detector. So I can run this kernel, or we don't do it like that, we do like this. Do you see that? That's it. That's my edge detector. And if I want to, so this is to x, this is with respect to x, and if I have it with respect to y, I will see something like that. So if I multiply these two, again in MATLAB you just create your kernel, then use IM filter, and then IM show. So you will see something like that. This is with respect to x. You see more of the vertical edges, and with respect to y you see more horizontal edges. And you can sum these two with the square root of power 2, and then you will have something that is visible on my laptop and is not visible there, which is basically all of the edges, if you look at it on your laptop screen. So with this simple equation, you can calculate the edges in your model. Scientists have come with kernels that you can use. They do a similar job. Pruitt and Sobel, these are two of the more famous edge detection models. You can run these kernels, or you can transpose them if you want the other dimension as well. And you can run these through images and detect edges, right? There are other filters, second order filters. If you take the derivative of a derivative, we will have filters again that are going to give you edges. So again, the equation is, if you use the difference approximations, you can have this one is minus x plus h to the right, plus 2 times the image minus I to the left over h, which is, if you can use this number differently. And this is what it comes to, minus 1, 2, minus 1. And if you have this over x dimension, and you have this over y dimension, transpose of it, and add these two together, you come up with this. 0, minus 1, 0, minus 1, 4, minus 1, 0, minus 1, and 0. So if you run this kernel to your image, you see the edges. Isn't it similar to what we did for sharpening? But that was a 5. So here we are eliminating the image. In sharpening, we are detecting edges, but we still have the image. We are sharpening the edges. Yeah? So here, so look at this, minus 1, minus 1, 4, minus 1, minus 1. And in sharpening, we had a 5 here. So the difference between sharpening and edge detection is that 1 in the middle of the kernel. So I'm eliminating the neighboring values and adding the pixel in the middle. So this is called a second derivative filter, which is called Laplacian as well. But the problem with these filters is that they enhance noise as well. So if there is a point that is different from its surrounding area, it enhances them. It detects them as an edge. It enhances them. In order to do that, one of the best or better edge detection models is log, Laplacian of Gaussian. So we do a Gaussian on the image, and then we do the Laplacian. So we have blurred the image a bit, and then we detect edges. So it eliminates those sharp noise areas that we have. So in MATLAB, you can just read an image, resize it to whatever size you want, and then say f a special log. And then you give it the kernel size that you want. It generates it automatically. And apply the filter. So this is what you will see, and your edges are enhanced. All right? So what we have done so far, we have blurred images by taking an average around each pixel. We have sharpened images by deducting the average from each pixel. We have detected edges by finding points that were steep in changes in brightness, by deducting the areas around them. So we have done some image processing. Now I have these areas, which is usually a good source of information for finding the objects that I'm looking for. But the problem with edges is that they are not a very reliable point. I want something more reliable. Do you remember the aperture problem we had? If you see through a small hole in the videos and you couldn't even detect the correct direction of the movement, you remember that example? Edges are not that reliable. Because if I move along this line, I will see no changes, right? Everything here is the same. If I move along this line, I see significant changes. Okay? But imagine this corner. If I move along this line, I see significant changes. And if I move along this line, I also see significant changes. So this corner is something that is a very good point for me to use to say this is a different object. If I find this point, I have this added value. So corners are considered one of the best saliency points, one of the best points that we also automatically detect them in our vision. We have cells tuned to that. We have cells in our brain that detect corners. And once we find the corners, like if you look at that door frame, you see the corners and automatically you have the idea in your mind. But if I only show you the edges, you cannot estimate how big it is. But if you see the corners, you get a very good idea about it. So corners are important, but again, not ideal, but important. In next lectures, we will see better features, but today let's go with corners. So this is a very important point. If you look at this point, small changes doesn't change anything to the values in the box. In this one, a small changes along the edge don't make any changes to the values in the box. But if you're like against the orientation of the edge, you see things. And in this one, any movement gives you significant changes. So this is a good point. Harris came up with a method in 1988 for detecting corners, and his paper has thousands of citations as well. We will have an overview of his model today. So the idea is if I have a point here, and if I move it, the values inside do not change, right? So this is not a corner. If I have a box here, and I change it along the orientation of the line, there is no change in the value of the box. So this is not a corner. But if I change this box anywhere, you see the values in the box are totally different, right? Do you follow? So the values in the box are changing every time I move that box. But in previous one, in the edge, it doesn't change. The values are always, if I change it this direction, they change. But other than that, they don't. So this one is a corner. And corners are important points. So we want to be able to find them. The basic idea is a Hessian matrix, which what it does, it has, you can take the trace of a matrix, which is LXX, LXY, and LYY. So what you do is you calculate the trace of this Hessian matrix, you calculate the determinants, and then you calculate the lambda values, and then calculate the R. If it's R over a threshold, you have a corner. It's a very smart way of doing it using this. So it says basically if you have something like this and this, you are finding a corner in that area, if this generates a value higher than a threshold. We will revisit this in lecture 6, but just have a general idea that corners are important. In MATLAB, it's very easy to find corners. So if I say I equals checkerboard 52, it generates a checkerboard for me. It's a function to generate this. And then you can say C equals corner I, and the method is Harris. So you give the input image, and then you show it, and then you can show the points that it finds, sees as red. So you can run this, and depending on which tools you are using, you can use this function as well, detect Harris features, which uses another toolbox. So there are different implementations for that in different toolboxes in MATLAB. And there are other methods, detect fast features, which we will have a look at on lecture 7, and they are also using a Harris model. So, actually lecture 6, I think. So, we have some ways to detect edges and corners. They are very, very important features, but for some of the tasks, they are critical. If you can find the corners of the eye and the mouse, you have a good idea of what the person is doing. If the eyes are like that, or if the eyes are like that, the areas, the edges, the differences between them, and you calculate those numbers. If the mouse is open, if it's like surprised, you can use that corner information and estimate the gesture.
And it should be fine to see what the corners of a sphere or circle within the clock. It should still be easily done.
Which one?
Oh, just on corner detection using this approach.
Yeah. You can just run it and it detects the corners, yeah. So what other features do we have? Is edges and corners everything, or do we have more features? Color sometimes is a very important feature, one of the important features, but sometimes it's a misleading feature. You don't want it sometimes. So again, it depends on your application. For example, if you see these images, you have these two apples and this banana, but if you don't have these two in your training images, then your model will not be able to say these are apples or bananas, because your model has never seen these colors before. So it's going to, also it is a banana, it might say it's an aubergine or whatever. So you have to be careful what data you have, what sources of information you are using. Sometimes it's a very significant thing in industry. The color of a product tells you, is it ready to sell, or it still needs time. In automated farming, for example, just a rough example, sometimes color of items change over time, and it could be a very good indicator of their readiness, or whether they are ripened or not. But in most applications, we don't need color. Like if I show you these images, you will easily be able to say all of them on the top row are bikes. Yeah. The second one are all cars. So you don't need color for most tasks. Color adds 3 times complexity to your programs, because now you're working on 3 different channels. Everything was 8-bit, now every pixel was 8 bits, now every pixel is 24 bits. So you should see whether color is really adding value to your work or not. Previously, in most works, they eliminated color because they said it's useless. My PhD, I proposed a new model to encode color into edge detection and saliency point detection, and it proved to be working. It added like 4% value. Nowadays, in deep learning models, most of the models are using color. So most of them, they have an input of 3 by whatever the size of the image is. So the input sizes are usually 3 by, say, 500 by 500. This is the way they read input images. So you can use color, and if you have a lot of images, usually your model is tuned. It learns how to deal with differences in color values, different intensities. So if you have 1 million photos of a hand, the color automatically becomes insignificant as far as it is in the range of the color tones for the hand that it has seen. If it sees a green hand, it says this is not a hand. It will be something there. But if it sees a black, brown, different races, colors, it will have it encoded. So it will still detect it as a hand. So in most cases, if you have a lot of training images, color is good. If you don't have a lot of training images, be careful, because sometimes color can be misleading. The other source of feature we can use is texture. So for texture, there is usually a repeating pattern. So something is being repeated in the pattern. Like if you look at this area here, there is a pattern of different colors, like that area. There is a different pattern. So it has a texture. And your models can use texture. One of the ways to use it is LBPs, local binary patterns. The way they work is they encode an area around the center point. So for example, if this is your area, you pick a center point and you find the values that it has in comparison to its neighbors. So I say 5, here is the center value. 1 is smaller than 5, so this is 0. 2 is smaller than 5, 0. 3 is smaller, 0. 6 is greater than 5, 1, and then so on. So I create a number, 0, 0, 0, 1, 0, 0, 1, 1, and then I convert it into decimal. So I say this area, I can explain this whole 9 pixels as number 19, right? I'm encoding that 9 by 9 values into one number. And I can do this for all of the values and calculate something like a pattern. In MATLAB, I put an example here for you. I'm reading one image, and I'm rotating that image. And as you can see, and then this is another image, an irrelevant one. So by using LBP, extract LBP features, and comparing the features that I get from this image and this image, I see a very good similarity between them, and not much similarity between these two. So LBP here is helping me to understand that these two images have the same texture. It's giving me orientation invariance. So these two images are of the same object but in different orientation. But is this enough? Or we will need more advanced features? Just a quick note on different image file formats. As discussed before, the raw format image, usually BMP, is a bitmap where each pixel has 24 bits, and you have 3 bytes per pixel. So if you have a 12 megapixel camera, you're talking about 36 megabytes, right? So it's a huge image. It's a lossless format. It keeps everything as is. But then we go through compression. Why do we do that? Because if I don't do that, if I have a video which is 24 frames per second of this 12 megapixel resolution, I will end up with 1 gigabyte per second. And you can imagine how much it's going to cost. And if you have a 2-hour video, it's going to be about 7 terabytes. Now add sound too. And if you have a 3D movie, it's going to be about 15 terabytes. So we need compression. We need to use formats that make things smaller, but visually the same. So one of them is JPEG, which is a format for compressing images. I'm not going through details of compression. It's not part of computer vision. It's more about signal processing and image processing. But feel free to look it up, see how they work. They are mainly Fourier transforms that are applied on images. So you have JPEG, TIFF, GIF, PNG, and for movies you have MPEG, AVI, and for sound you have MP3. So you remember the revolution MP3 started. Like you had a CD track which would contain 10 tracks, but with MP3 you could just automatically listen to 10 hours of tracks. So it made a big revolution. The same happened with MPEG and JPEG. Now let's say I have some images and I want to stitch them together, building a panorama, one of the functions that most cameras nowadays have. What do I need to be able to stitch these images together? I need features in those images that are reliable, that I can find and match them. Also, there are different small rotation, different scales, different sizes. So I need something that is reliable to be able to build a panoramic image. So for an example, I have these 2 images of a mountain, and I want to combine them together. What do I look for? As I said, by eye, I see these 2 are the same. So I put this area next to this area, right? So if I crop this image, let's say here, and add it to this one, I have a bigger image. But how do I do it by computer models? I need features that are reliable. One method is to use corners. But if I find corners, I may find thousands of them. How do I match them? Impossible. The other thing is finding corresponding points. If I have a corner that is like this and in the other image like this, they won't be the same thing. They won't match, not in a million years. So I need some points that are reliable and I can use them. As I mentioned, the best way to do that is corners. But we need to add more features to these corners. We need to make these corners scale invariant. We need to make them rotation invariant. So if I find a corner that is this size and this size, my model should be able to say this is the same corner. We haven't learned that today, but one of the models suggested for this is called SIFT, Scale Invariant Feature Transform. We will talk about it in lecture 6, but now you have a general idea. I can make it a scale invariant. How do I do that? Again, same question with vision, with detecting eyes, faces. I create a pyramid of scales. How do I make it rotation invariant? There is a small trick. I find the dominant orientation, and every feature I find, I translate it to that orientation. So I translate this, and I say, oh, these 2 are the same. I have different scales of this and that. So the idea of SIFT is very simple. It's something in that line, but we will go in more detail about it in lecture 6. Here is an example in MATLAB website, MathWorks website. You can do feature-based panoramic image stitching. So it detects features, SIFT, SERF, FAST, different models for features. It shows you how to do that. It detects features if you're in a rush, or otherwise we will reach that in a few lectures. So you will be able to find reliable and distinctive descriptors. We call them features and image descriptors. Once I have those features that are reliable, I can represent my image as a combination of those features. I can say that in a cat image, I see this feature, for example, and in a dog image, I see this feature, or whatever. And then I convert this into a feature vector. I convert this into a feature vector of no matter what dimensionality we are speaking. Let's say 10,000. I have 10,000 features in each of them. And now I find a line. This is called classification. You can do that by support vector machines, artificial neural networks, deep leaf networks, deep neural networks. There are different ways to go around it. We have unsupervised learning. In this case, I know these features belong to a cat and these features belong to a dog. I have labeled images. In another case, I don't know. I have some images. I don't know whether they are cats or dogs, but I find some similarities between them. I see, oh, look, the images of cats usually look like this. The images of dogs usually look like this. So I group them together. I say these are group 1, these are group 2. This is unsupervised learning. We will get to this learning in lectures 5 and 6. One about supervised learning and one about unsupervised learning. And we will learn about more feature extraction models and CNNs, which they are a classification model, and they also build their own features in line. They don't use external features. There are some webinars on MathWork website. So if you are interested in face recognition, which I assume you all are, you can watch this 1 hour video and it does your coursework for you. So, not really, most of it. So if you open this link, it just explains what you need to do and the steps that you need to take. And here is a good example of object detection and tracking on MathWork. So next session we will be talking about image segmentation. And the last slide of the day is about your coursework. So the due date is approved 1st of May, but in your mind try to make it like 2 weeks earlier so that you have 2 extra weeks. And it has been released. The images are uploaded online. You will see them in very different formats, shapes. You will be dealing with real-world challenges of data collection. So it was a very simple data collection. We were like a few students together, took some photos, and we have some folders. So you will see you have to put them into different folders. You have to prepare your data. And that is part of your coursework. One of the more important parts of your coursework is your report. Start writing it. Say whatever step you're taking in creating your data set. So what do you need as a start? You have these folders. Let me show you what you will see when you go to Moodle.